Hello, my name is Justin, and I like map projections. Behold, the Earth. It's a sphere. And these are maps. They're planes. But wait a minute! Alaska isn't that big! And South America doesn't look like that! Because all map projections have distortion. It is impossible to map the spherical Earth to a plane without distorting something. But what to distort? And how much to distort it?
A technique of dimensionality reduction, or multi-dimensional data visualization, is using a series of springs in your higher dimensional space to connect points that are near each other, and then taking those points and project them onto your desired dimension, and then releasing the points and seeing where the springs take them. This allows points that are near each other to remain near each other, and for a lot of the structure of the higher dimensional space to be preserved in your lower dimension. Let's take a three-dimensional sphere and map a bunch of points to it, and then connect those points with springs. Now, in order to project it onto the plane, we'll have to slice it in some place. This balloon just so happens to be both a spring and a sphere. But in order to map it to the plane, we have to slice it. Now, this balloon is of uniform spring constant. So when we map it to the plane, all areas will need to distort fairly evenly in order to really get a good mapping. But let's say some of our areas, such as areas over water, had lower spring constants.
So, you want to model a sphere as a bunch of springs. How do you do that? With a geodesic grid. What's a geodesic grid, you ask? It's a method of modeling a sphere as a polyhedron, or in our case, a polynodal spring mesh. Here's how you do it. Step 1. Take an icosahedron. It's kind of like a sphere, but there's a lot of room for improvement. Luckily, each of the faces is a triangle. You know what triangles are really good at? Becoming 4 more triangles. So what if we just replace every triangle with 4 more triangles? Whoa! That's like more of a sphere. What if we did that again? And again? That's a pretty nice spring system you've got going on there.
The problem with the spring mass damper system is that you have springs and masses and dampers. In actuality, the main issue is that the masses can develop momentum and overshoot a local minimum. We need to develop a better method of solving our maps. Gradient descent allows our system to always move towards lower local potential and not produce kinetic energy, so we can find the map more precisely and faster. We also don't have to fiddle with dampers to get it to run correctly. Here's a simulation using gradient descent.